Okay, so just as a brief introduction to some of these properties, we've already talked about these. Go back. We've already talked about these. These properties are not useful necessarily for condensing and expanding logarithms. These are useful for evaluating logarithms, simplifying some logarithms that we may see. Okay, if you don't have these written down, pause the video, write them down. Miracles of technology. Okay, but as far as expanding and condensing logs, these properties all stem from, see if I can expand this so you can get to the bottom easier. These properties stem from the fact that logarithms are exponents. Logarithms are exponents. They are the inverse of an exponential operation, but they are exponents in and of themselves as a definition. So we can rely on some of the properties of exponents that you've learned in your algebra history, and that is the product of two exponential terms. If I might just add real quick to this, if you did x to the m times x to the n, two powers that are being multiplied together, we can turn that product into a statement involving a sum. In other words, we add the exponents when we're multiplying the terms. The same can be done for logarithms. If you have a logarithm and inside that logarithm is a product of any kind, you can write that as a sum of two separate logarithms. So when you talk about expansion, this is how we can expand one log into two. When you talk about condensing, you do the opposite. If you have the sum of two logs, now emphasis on the fact that the bases have to be the same, but you can take two logs that have the same base and write them as one with a product, right? The rest of these follow suit. When you divide exponential terms, you subtract their exponents. So with the logarithm of a quotient or the logarithm of a fraction can become the difference of two logs. Listen to the nomenclature, listen to the verbiage, the words that I'm using. The logarithm of a quotient, or the logarithm, singular logarithm, of a fraction. Inside of it is the fraction. I can write that as the difference of two logs, and vice versa in the opposite direction. Because a logarithm is the inverse of an exponent, if we see an exponent within a logarithm, so whatever's inside the logarithm, if it has an exponent, we can undo that. We use this property to help us solve when we're solving exponential equations. Taking the logarithm of an exponential term will move that down onto the quote-unquote first level of the problem. This last one is the change of base formula. I mentioned this the other day. TI-inspired calculators allow you to plug in the base. So in the past, if you had something like this, okay, you would have to use the change of base formula in order to evaluate, to find an actual value, right? So if you look at this problem, the change of base formula is something that helps us evaluate logarithms with obscure bases, like things that we're not used to seeing, like 3, for example. Normally we see log base 10, or we see natural logs, okay? In this case, log base 3 of 2. You wouldn't be able to type this into a TI-83 or a TI-84 calculator, okay? But through using some of these other properties, you can convert this into the quotient of logarithms. Notice the verbiage here, okay? The syntax of the words. This is the quotient of two logs. This is the log of a quotient. So down here, if we wrote this, you take whatever is inside the log, you write that on the top, and you take the base of the log, you make that the bottom. These are now base 10 logs, which many calculators are capable of executing. Okay? All right, let's go to work.